Hey, good morning, everybody. My name is Chris Doty. I'm with Amazon Web Services. I help cover the DoD through the Air Force, SOCOM, CENTCOM, and some of the other COCOMs. I have three, housekeeping items I need to take care of. If there's anything that happens during the session, the emergency exit is the entrance that you came in, back to the left. Restrooms are out the door to the left. And at the end of the session, there will be a survey that we ask everyone to please fill out. So the session we have this morning is around IoT. We have one of our more innovative partners that has put together, I think, a very interesting presentation around taking some off-the-shelf items that any DoD customer or any civilian agency customer can go out and acquire and put together a very slick IoT solution leveraging some of the AWS services. Let's see what we got here. So I'm going to go ahead and hand it off to Stephen.
Okay, thank you. So just to kick this off, a quick agenda. I'm not going to necessarily speak to this, but this is kind of the rundown of the presentation. And oops, did I go backwards?
You did.
I did, there you go. So just to kick this off, we're from Novetta. Matt and I are from Novetta. Novetta is a global or a government services firm who primarily serves the intelligence community, DoD, law enforcement, but we have a broad base of government customers, public sector customers, even a few commercial customers. And if you were to ask us what our kind of core competency is, it's solving hard problems for people who have a real mission need. And along with that comes a level of agile expediency and kind of rapidly taking something from ideation into something that a mission can actually execute with. And so how we got into this IoT space is about a year and a half ago, kind of broad number of our customers started coming to us and saying, hey, we're really behind the curve here on this sensor revolution. We have this big gap in whether the people are, whether we got three guys on a hilltop in some remote area or we've got a gigantic installation someplace. We have this gap where we can't sense that area of interest. We're not analyzing that data, and we're definitely not capable of getting it kind of into that frontline operator's hands so they can leverage that insight. And so to me, it was music to my ears because I'm that guy that has been, that friend you have who has been predicting that their football team is going to win it all for 15 years. And then finally they do, and they're like, victory, right? So I was a little bit ahead of the curve. I've been predicting this thing for about 4 years, and I guess finally I'm right. But as we started talking to them, one of the first things we realized we needed to do was to define that problem, right? So what is IoT? That's a little bit wrong. There we go, we fixed it. And so dad jokes aside, why is Internet of Things different than these kind of sensor SCADA platforms that have been around for 40 to 70 years, depending on how you want to count it, right? We've been putting sensors out in the field, collecting that data for a long, long time. What makes Internet of Things different, and why is it more powerful, right? And so the pat answer to that question probably focuses around cheaper, faster, smaller computers, power supplies, and networking equipment, and the ubiquity in that network equipment means that we can put more sensors both vertically. We can put more sensors in more stuff and kind of blanket our area of interest in sensors. And then that area, there we go, can be more places. We can push that out across the globe in a good way. Having said that, I think that is an easy answer, but I don't think it's a complete answer. So when we talk to our customers about the power of IT, they're not talking about 5,000 ground sensors, streaming seismic data back to some blurry-eyed analyst, right? They're talking about taking those 5,000 unattended ground sensors, mixing it with 5, 10, 15 other sensor platforms, and kind of aggregating, synthesizing all of that data, throwing in some social media data, some news media data, intelligence reporting, kind of putting that all in a big bucket analyzing, synthesizing, and then extracting insight out of that is kind of deeper and faster than what a normal analyst could do if all that data just kind of came streaming into them. So the kind of bottom line here is what makes IoT more powerful is that data is really king. And we're really discovering that holistic aggregated data and our kind of modern compute and modern algorithms really make data king and make us kind of, the IoT revolution is this kind of a bunch of painful, hard engineering to get more inputs that we can analyze, right? So that is, now I'm a data scientist, so I might be taking this a little bit far, but for us, really, IoT is just another step in that data revolution. That being said, right, I talked about all of the kind of sensor platforms that have existed for 40 to 70 years before that. We can't get rid of those, right? So if we looked at those early adopters, right, there's some really robust technology here. There's a bunch of industry standards. There's great hardware. The problem is when you look at those kind of legacy technologies, each one of them probably has a fatal flaw that makes them imperfect for that holistic kind of aggregated data set. But that doesn't mean we want to throw the baby out with the bathwater, right? We want to be able to stand on the shoulders of these giants, but just take it another step further. And so if we think about those kind of three things, we have something that approaches key performance parameters or operational objectives or really kind of stuff we want to do with IoT. What does make IoT different? Well, it's that proliferation of sensors, the ability to aggregate, analyze data, and then it probably also includes being able to leverage all of that existing technology that is in place, not just because it's already there, but because there's good stuff there. It just needs to be taken to that next level. So that kind of sets the tone for what we operationally want to do with IoT. The kind of next step, obviously, is to start to build technical requirements around these KPPs, right? So what does the perfect IoT for our customers and probably a broad base of government and public sector people require, right? So the first thing is we need this thing to talk to anything, right? So whether that's those old industrial platforms that speak Modbus or CAN bus or OPC-UA, any of those kind of long-lived industrial standards, or the new IoT space with MQTT and JSON and those kind of smart languages. We want to be able to talk those. And furthermore, we want to be able to kind of find a new sensor, a new innovation that speaks its own unique protocol. And we want to be able to develop a connector or adapter for that protocol really quickly so we can integrate that with not a huge barrier to entry into our broader platform. And so this will also be a trend through most of these requirements. If you think about IoT and the fact that we could have tens to hundreds of thousands of devices dispersed globally, you need a mechanism by which we can take the whatever we develop, that new sensor connector that we've just developed, and in an enterprise way, in a managed way, in a reliable way, we can push that out to that whole global network, right? And when you think about kind of IoT sensors or even the kind of like laptops of today, that is a tough problem. It becomes a kind of order of magnitude harder when you start to talk about this kind of broad things network. And so we definitely need to spend real time thinking about that. And then the final thing is standards exist, right? So there are standards out there, and we probably, if we really want to do our job well, we want to be able to represent all of those downstream sensors that kind of come into our Fusion box and into our platform. We want to be able to represent them as compliant devices, whether they're compliant or heterogeneous or not. We want to be able to, for instance, say, hey, all of these disparate sensors behind us, they now look to like a COP or some other platform, like for instance, Army's ISA standards. So they'll look like compliant devices for kind of any upstream system that speaks Army's ISA. So the next big kind of requirement is we want to be able to analyze anywhere, right? This is the kind of meat of how we get from kind of sensor platforms of yore into IoT platforms of today. And And what we mean by that is we both probably want to be able to do little analyzing on kind of small microcontrollers, but then push that edge computing. If we've got a Connex box full of GPUs, we want to be able to do big machine learning or object detection type algorithms on streaming HD video. And furthermore, we want to, again, back to that theme of kind of enterprise IT management that is baked into this IoT problem. We want to be able to take those kind of business rules, right? Whether they're simple, finite state machines, graph trees, where if 2 of the 3 sensors go off, I throw an alert, but one of them won't trigger, all the way to complex machine learning algorithms. We want to be able to develop that in the cloud, and in a managed, reliable way, push that out to our broad network, and then probably also make smart choices about, hey, I'm not going to push an expensive machine learning module out to a Raspberry Pi, but I am going to push it out to that Connex box. And you're going to want that kind of flexibility and that management capability. The next thing is, so again, when we're talking about pushing into remote areas, we need these platforms to operate in any state, right? So that means, hey, a lot of the times, what my MANET or my LAN is going to be completely disconnected from anything outside of it. It's going to be in some remote area, and we need that platform to be able to collect this data, process this data, and then do what kind of the computer science problem is the eventual consistency problem, right? So these 2 devices have been separated from each other. They haven't talked. When they come back together and talk, they need to kind of get together and figure out ground truth of what happened to the 2 of them while they were separated. And so you've got to solve this eventual consistency model, and you have to solve that at scale. And so that's really kind of one of the crux problems we have when we're talking about operating in any state. And then finally, especially because we're government and public sector, but just generally, right, we need to secure our mission needs, right? And security, even with IT platforms, can be complex, and especially when you move into a global IT platform, it becomes even more complex. And then when we talk about these kind of intermittently connected devices and this kind of heterogeneous network and all the complexities that come with varying levels of compute, you need a kind of a robust platform to do all the proper cybersecurity stuff you need: continuous monitoring, updating, patching, firmware updates. And you need a mechanism by which you can kind of handle the heterogeneity of the platform. So then the final thing that we need to handle is we need this thing to scale, right? We talked about the kind of varied customers we have, right? And some of our customers were very interested in a few people in a remote area being able to sense, the 200 meters around them. But we don't want to give them one thing, and then as we scale up to a forward operating base or to a small area, all the way up into a grand installation, we don't want to have to give them something different every step of the way. We want that kind of little component disconnected thing that the 3 people rolled in with to begin with. We want that to be one of the Lego blocks that we built this grand sensing platform with. And that key component is still in there someplace in that broader network. We were just adding stuff, and the thing fluidly scaled all the way up to the level we need it to scale to. So that kind of covers both our operational needs and then what we would be, when we kind of sat down and chalkboarded this and came up with our whiteboarding sessions, right? The kind of key requirements, the key epics that we wanted to achieve when we designed an IoT platform. So that brings us to a big question, which is, like, why are we here at AWS? What is AWS? What's AWS's role in this perfect IoT platform? Well, to be honest, AWS basically does their AWS thing. They just do it in this IoT space. I'd actually argue that they turned it up to 11 into the IoT space. And really what they've done, what they always do, which is to give us pipes. Give us all the hard, complex crap that you would have to develop to make this platform work, but isn't the kind of cool, sexy stuff that we would normally think of, right? They do all the hard work and heavy lifting, and really in many ways, especially in this IoT space, I really think they've made the easy stuff we don't even have to think about. They just do it for us. They've made hard stuff easy for us, and they've made us kind of the impossible stuff you wouldn't think you'd be able to do, and it would take years and years to develop. They've made it something that we can probably rapidly deploy. And so just to dig into that a little bit. So again, if we look at our kind of 5 key requirements, what does AWS bring to the table when we're talking about this? Well, if you think about that first thing, talk to anything, we need a connector framework, right? We need to be able to, we need to have connectors out there so I've got my Modbus devices, they're speaking some language. I've got to convert that into a universal language so I can kind of store that and be holistic about it. Well, Greengrass with its connector framework gives us a mechanism by which we can develop Lambda functions in the cloud and push those down to our entire Greengrass base. And now we've got a brand new connector. And we didn't have to worry about making sure that service stays alive, what protocols to run, all the kind of heavy lifting of the kind of socket programming and everything like that is basically done for us. They even give you kind of an easy lift to get into the GPIOs of these devices or into the serial networks of those devices really easily and quickly. And then back into how we speak to anything, something like Amazon's API gateways allows us to, again, just focus on the translation. So just focus on taking the kind of data that's sitting in our data store from all of those heterogeneous sensors. And all we have to do is figure out how to get that language into ISA platform. We don't have to deal with all of the other stuff about standing up an API gateway, right? So then, if we talk about analyzing anywhere, well, the great thing about Greengrass is we can, it interacts perfectly with all of the kind of core AWS resources, from SageMaker to Recognition to kind of graph databases in Neptune. They even have a kind of a specialized machine learning platform called AWS IoT Analytics, which kind of does anomaly detection for your sensor arrays. And the nice thing about that is not only does that allow us to kind of develop things in SageMaker and develop things and leverage that kind of stuff, they have a mechanism by which I can push that down into Greengrass devices and onto Snowballs and into these kind of edge devices. So now I can write my business rules or my machine learning algorithm, some central location, again, back to that theme, right? And I can deploy that out to my global network. I can test it. I can do feature flags. I can roll it out sequentially. All that stuff that we kind of CI/CD stuff that we've grown to kind of love with our IT platform. This gives it to us for our IoT platform, which, right, isn't anything magical I've talked about regarding IoT, but gosh, is it needed if you've got 10,000 devices sitting out around the globe. Lastly, that operating in any state, that tricky eventual consistency problem, right? That is a thing that there's been lots of white papers written about. Lots of stuff has been talked about with that. The databases struggle with that. If we were to develop from scratch an IoT platform, that would be something we'd spend a ton of time on and probably not get right out of the box. Amazon has handed that to us in a really robust way for free, in a really flexible, broad manner. And that just really, I mean, in many ways, almost more than anything else, that kind of disconnected, intermittently connected model that they give us, which allows us to kind of have those two talking heads connect in a secure way and exchange information, is maybe one of the most powerful things they provide to us.
Questions at the end? Or
yes, yep. Okay, so then finally, securing that mission. Again, we have IT security. We all need to get our ATOs or go through some cybersecurity practice, right? Well, AWS for IoT platforms, we have, like Novetta definitely has, a bunch of mechanisms where we have all that continuous monitoring, all of the patch management, all of the updating, all of the scanning, all the STIGs and all of that stuff built into our IoT platform. AWS makes it easy for us to extend that into our IoT platform, right? So you get all that goodness coming from AWS core services, and we get that connectivity model, that secure connectivity model, where we can then monitor those kind of disparate devices out across the globe. And then finally, scaling to any size, right? I think this is going to sound really redundant, but again, Greengrass works just as effectively on a free R2OS microcontroller as it does on a big Snowball or on a Connex box. And then all of the Amazon core services that can scale, from EC2 scaling to the fact that we can use Lambda functions that just can essentially scale infinitely. So every time a sensor does something and we want to trigger a job out of that, that naturally works and kind of can work both on the edge and in the cloud for us. So that really does give you kind of the high-level overview of what we think you can derive out of IoT, how we would design the perfect system, and then how AWS makes designing that perfect system a lot easier than it would be, and why we think the combination of our brilliance and AWS's resources really makes it so we can rapidly deploy this stuff. What's left? Well, we probably have to prove it, right? That was some bold claims. So what we did to kind of prove the expediency with we can put together real end states, we decided we would take 2 engineers, give them a month, an absolute greenfield. They couldn't have anything in place before they started. We gave them 2 scenarios, and we said, what can you do with regards to those 2 scenarios that look a little bit like what our customer base is asking for? And Matt is going to kind of give you the rundown of what we were able to achieve in that month.
Thanks, Stephen.
No problem at all.
So my name's Matt Johannesson. I wear 2 hats at Novetta. One is managing our alliance with AWS, with the wonderful partner team here in the front of the room. And also, I report to special projects doing operational prototyping. So I'm actually going to switch to a video, and bear with me while I do that, of how we built this prototype. So just give me 1 second. So the 2 engineers, in this video, I'm actually one of them. The other one's in the room here at the front. His name is Felix. And what we're going to do is give you some of the under the hood of how we built a prototype to monitor something like an intersection with extremely cheap sensors. Show of hands, how many people have seen a Raspberry Pi or used one, turned one on? Awesome. Most of this will be motherhood and apple pie. So here's our scenario. We've got an intersection on a wonderful piece of property, private property. And we're going to set up our prototype, which is basically a Raspberry Pi, a motion sensor, and a camera. We're going to use Greengrass, as Stephen mentioned, at the edge to basically do some basic analytics from those sensors that anybody can buy anywhere. So this is meant to look like a prototype because it is a prototype. We do a lot of this at Novetta, where we take a complex idea and we just begin. So this is literally a Pi hung from a branch in a tree with paracord. This is something that we think folks that from our mission spaces can relate to, because often they have to improvise on the fly. How many people know what a GPIO set of pins is? Okay, most people. But for the people that don't, it's basically an easy way to connect sensors. So that little Pi can have 2 sensors, 3 sensors, 4 sensors, and then you can very quickly take the data from the sensors for under $100 and start sending messages to something like an MQTT queue on a Snowball. So what does that mean? We've taken our platform and we've pushed it to the edge. We could use it in the cloud. Now what I'm going to do here is pause and just go over this architecture for a minute. Those Lambda functions that communicate with all of the other services, they can be developed centrally. They can push messages to various queues, whether it be at the edge or in the connected cloud environment. We're also using something called ATAC, which is a favorite COP tool built by AFRL that helps us with visualizing the data from these sensors. It's a very common thing used for base protection and force protection. So what do we have? We have our sensors set up. Now the engineers in the field need to monitor the data that's coming off those sensors. We have the ability to iterate very quickly because all of this can be deployed, again, at the edge. We can push updates. We can look at input, output from the sensors. Here, Felix is actually looking at ATAC itself on the interface, making changes on the fly. We're replicating a process here that we don't always understand every variable in every environment where these would be deployed. So open source tools like Jupyter and Python are favorites to be able to tune how these interactions between sensors work. So as the engineers start to figure out the lay of the land, how their setup is working, and again, they're using a portable power source, a Raspberry Pi, and a couple sensors. So when eventually the third actor in this film shows up, a vehicle, the sensors start generating output. And you see the output is basically JSON messages. In this case, it's actually a machine learning model that a Lambda function creates a message that gets sent to the COP tool. When we have connectivity, we can use recognition. We can actually get more complex data from that image. We expect to see more and more models being deployed to the edge. In one case, we might want to look at a license plate. I'm going to just pause it there for a second. So in this particular scenario, it's not the actual license plate. Maybe my mouse will work. I want to go back just a little bit. Sorry about that. There we go. So when I have text data out in the field and I have connectivity, I can actually use recognition to pull the text off of something like a license plate. You see the highlighted text at the top? That's a very accurate bit of text that was extracted from a simple square that was overlaid on top of a video. Recognition is incredibly accurate for character recognition, and this is just one way that we can use it. So as we continue to progress, you might say, well, how do you use that information? Well, one of the demos that we're doing this week here at Public Sector is all about our new partnership with Unveil. I don't know how many people in the room have heard of Unveil? A few, good. For those of you that haven't, they specialize in something called homomorphic encryption, which is basically one-way encryption that allows us to deal with sensitive data with never decrypting the information. So how can we use it in this scenario? Take that license plate example. We can feed the information into a machine learning model that helps us understand what that vehicle is doing, where it came from, and cross-check it with other potentially sensitive information like a watch list. Okay? We can then tip and queue over a secure channel to other parties that might care that that particular vehicle has showed up in that particular location. If you guys have any questions about that, please see us later at our booth. We can show you an in-person demo. So as we go, just start thinking about all the different machine learning models you've heard about, how they could be deployed at the edge, in combination, working in concert with sensors. Think about how engineers should tune these things to improve continuously. The barrier to entry here is not that high. It's all about how you use the sensors. It's how you do the analytics. So in this case, you're looking at ATAC on an iPad from 2 sensors as a truck rolls by, and we put that together in just a couple of weeks. But now how do we scale it, right? Stephen mentioned we have to be able to add sensors. We have to be able to mature. So the second scenario is all about a fence line. Right, so the first scenario is a little bit about setting up anywhere to monitor some kind of situation. This is more toward that installation perspective where we want maybe better fixtures for the sensors. We want better combinations of how the sensors work together. So for our chain link fence example, the idea here is that we've matured a little bit. No longer do we have paracord hanging the Raspberry Pi. We've actually 3D printed some fixtures for the fence. So we figured out, hey, how do we want the sensors pointing? Do we want 2 motion sensors? Do we want 1? In this case, we had 2. And the stack that Stephen explained allows us to very quickly add those sensors. This could be 10,000 motion sensors. It would all work the same. They're going to post messages to those queues. AWS allows us to scale automatically. It doesn't matter if it's 2 or 10,000. So in this particular example, we've also added a thermal camera for, again, under $20, right? And we've added a vibration sensor. And what we want to do is start tuning the way these sensors generate the output. So for example, if 2 of the sensors trigger, we're going to get an alert. It's scary how good these thermal cameras are, by the way, for under $20. You can see a silhouette of a human in that shot from about 50 feet away. So again, new sensors added, same architecture. We haven't made any changes, and our goal is to actually put information onto ATAC to make it readily available to those in the field that need to deal with it. So here's a picture of the vibration sensor. This guy's name is Brian. As Brian climbs the fence there, he triggers the vibration sensor. We get an alert. In this case, he's going to try to go over the fence where he's not going to trigger the vibration sensor, but he's going to trigger the motion sensor. So those messages, again, are being sent to ATAC over secure comms with MQTT, and we have the ability to add models at the edge to get better insight. That's it for me. Chris, do you want to help us wrap up here? I'll put the slides back up.
You bet.
I can get my technology to work. there it is.
Yeah, so it's probably 6 to 9 months ago, I guess, when Matt and I had, kind of our initial meeting, started comparing notes around some of our customers, what they were looking for, where Novetta brought some innovation, some of the challenges that we were facing, where they could help backfill or fill in some of those, and we started touching on Raspberry Pis. I have a lot of customers that are always looking to repurpose either some very inexpensive items. You can't always go out, as everyone knows, and acquire some heavy technology or some expensive technology. So some of the special op forces guys are always looking to, how can I take advantage of something off the shelf or some commercial item and make it into a solution. And so Matt and Steven were already actually working on some of these items. So we've taken some of this, they've actually enhanced it quite a bit, as you've seen through the architecture that they put together, and made this much more scalable. And I think there's a lot of interest around, at least my customer base, and looking at these things to actually field. The ATO process on some of these things is actually pretty easy for them to go through. So, from that standpoint, I think any questions at this point? I think we've got 20 minutes left.
You had one, sir? No.
Had a question up front maybe earlier?
No, you kind of answered it, but this looks a lot like a ground station and something that NASA would do, but just deployed on the ground instead of space. Or my name is Scotty Myers. I'm from Petascale Computing.
Yeah.
This looks a lot like what NASA would do. You're doing it on the ground, terrestrial. Yep. NASA is going to need to do the exact same thing in space because of the hundreds of thousands of satellites that will probably be blanketing the air. Are you working directly with NASA now to take their methodologies? Possibly, they have a very, very good suite of methodologies. That implement that along with what you're doing could be something that's really amazing.
Yeah,
Thank you.
I think it's that NASA problem, right? When you think about satellites in space, you absolutely need that enterprise management, because it's expensive to get someone up there to patch the server, right? And so, right, and so it's cheap, light, well-managed infrastructure, right? And it's exactly what this model is made for. It takes that and it takes it to a whole nother level, right? But I think that this methodology seems perfectly suited for that problem set.
Cheap is good.
Yeah, cheap and light, right? You don't cost more money to, and.
Yeah, I think one of the things we saw even here this week as we were putting the demo together, speaking about light and fast, when we got our demo set up, which is a Pi camera at our booth taking photos of cards you can hold up in front of it that look like a license plate. The model that we had deployed on the Snowball Edge wasn't doing very well with the conference environment because we didn't have training images from the actual environment where we set up the camera. So the team was able to very quickly retrain the model in line and redeploy the model without too much effort at all. Maybe 15, 20 minutes. They then even tinkered with SageMaker Neo to take the same model and redeploy all the way down to the Raspberry Pi just as an experiment. They'd never tried it before, but we made it work. It's very light.
What's interesting is in 2014, I submitted something and it was beat out by the 3D printer on the moon. So when you look at your model and you look at the fence and you said, oh, okay, I just printed this out. Well, the next thing people are going to be doing is 3D printing in the field, in the theater.
Yep.
So
Already are.
everyone will be printing either weapons or sensors. So when I looked at your design, it was all pushing from the left to the right, but you're going to need something to push from the right to the left to morph and actually create sensors on the fly. So that's what
Yeah, and to take that even further, right? So not only are we likely to be 3D printing and kind of taking over mechanical engineering with that 3D printing, what we'll call additive manufacturing, but you're likely also to take over electrical engineering as well and stop going and saying, hey, I'm going to go to Eagle and build a board, and then I'm going to ship that to a fab plant, and they're going to print out 500 of them for me. They're already starting to kind of find economical ways to basically 3D print PCBs or use kind of that 3D print technology. So you're building boards on the fly. And so like you could imagine, to your NASA example, you could imagine having the ability to replace boards, like a system up there in space with the ability to replace the board, pull it out and put a new one in that works.
Yeah, and to add to that, one of the things I've started talking to the team about is that from a software perspective, the machine learning models that you can use to do the analytics are a lot like a sensor, like a modern day sensor, where you can actually push multiple versions of the same model or individual models to start chaining these tasks together. So for example, in the video, you actually saw output from a local machine learning model that identified that there was a truck in the video. We had no connectivity whatsoever to recognition to do that triage step. And then when we do have connectivity, we can start using some of the more friendly cloud services. But having the ability to build your own triage models like that, you can actually create synthetic sensors that run locally on the devices.
So we see algorithms being flown into the field.
Yeah.
We see 3D
Yep.
printing models being flown into the field.
Mm-hmm.
And of course, thanks so much.
No problem.
Yeah, and just one more point on that, we really, at Novetta, we really understand the importance of having a library of things like machine learning models, where depending on the mission needs, we can take those models off the shelf and deploy them to the different stacks that are needed in the field.
That's going to require a whole new breed of security.
Mm-hmm.
Yeah, agreed, right?
Because the danger of 3D models and high-end billion-dollar algorithms are going to be something that
Protecting that IP would be, yeah. Did we have another question over here?
Sorry.
Yeah, go ahead, sir.
See, the most problematic problem, in IoT is the security.
Yeah.
I don't know what kind of, you just encrypted?
Yeah,
Because
so
you have low power device, low CPU, and
Yeah.
so forth. So I'm talking about smart city and big applications.
Yeah,
and
what
so
do you do?
forth.
What do you do with
Yeah, so
like
what
a
did you do for
microcontroller?
security? Because
Yeah.
that's the big problem for scientists right now.
Yeah.
So really, it's unsolved problems. Still, there's a lot of problems. You can hack it from any weak point. So I want to see what you did.
Yeah,
you can
so-
make it work, but the security is the most problematic one.
Yeah. So remember, and I say this a lot, when we talk about IoT, we talk about radios, we talk about a bunch of stuff, right? We're talking about a computer. At its bottom line. And so when you talk about those kind of really low power computers, a microcontroller that's, an AT-Tiny 85, there's not a ton of compute on there. Oftentimes, one of the trade-offs we have to do is we have to use AS128 instead of 256 because there's just not enough compute on the board to do 256. So there's two answers to that question. Number one is it's still a computer, so I can still use certificates, and I can still do static code analysis. And the nice thing about those small machines is that the code that they deploy is relatively simple. And so in many ways, and I think this actually, as a kind of a cyber guy, this goes across all of cyber. Hygiene is about 95% of cybersecurity. So if you've got something that's hygienic, well-developed, it doesn't have bugs, you don't have to layer all this extra stuff on top of it because all that extra stuff is just to make sure that you didn't do a bad job to begin with. And so the nice thing about those platforms is that they're simple, lightweight, we can really examine that code, but then also they're simple and lightweight and that code is small. And so with like an enterprise platform like AWS, as long as we got the mechanism to update the firmware on that machine, if we do find a bug, we can, through an enterprise mechanism, through that greengrass device, we can reach out to those little tiny kind of low compute devices and update their firmware in a manageable way. But and then that interconnectivity of them, right? So I've got some sensor that sits out there and it's disconnected most of the time. We have to have a mechanism by which, as soon as it comes back online, we update that firmware, we rescan it, we remake sure that it is kind of maintaining its cybersecurity, and we probably rotate its encryption key to make sure that we've got that kind of new level of encryption going on. So just in case it was compromised in the action, right? Does that answer?
Yeah, just to give a little bit, because we're working with this one in our university.
Yep.
You see, the issue, we're trying to harden the device itself.
Yeah.
To make it secure by itself.
Yeah.
And we use some different, I don't know if you heard of IOTA and others,
Yep.
because you need low power and we call it cheap, is not, it does not need a huge, or storage or something like that.
Right.
So harden the device. I'm talking about communication. You can do that, the encryption, but
Right.
the problem, you can hack the device itself.
Right, yeah, but that, I mean, in many ways, the hardening of that device comes from good software development or good firmware development on
Right.
that device too, right?
Yeah, I don't know. Just asking about AWS.
Yeah.
Are there any, work in that one and the
So
security,
really where
cybersecurity
AWS
and
would
so
come
forth,
in is their ability to update that firmware, to interact with that device, and then to do the kind of enterprise management stuff revolved around that, right? So check to make sure, hey, this device has firmware on it that is 2 revisions behind and there's a vulnerability in that, right? Not that I know, but AWS isn't going to, they're diving into free RTOS and things like that, but that minutia of making sure that the end device and those low compute end devices are secure is false to somebody like Novetta or the OEMs really, and really probably us working in partnership with OEMs, which we've done before on some of the kind of government platforms, to make sure that device has that hygiene, but also the physical security around it. So, right, we've got that, not to quote regs, but FIPS 140-2 level 4 kind of, so when you open that box, the zeroization happens and things like that.
So I'd add to that as well. We've been doing a lot of work with the Snowball team through our partnership to extend the power of things like EC2 and S3 to the edge. So if you think about the cheaper, lighter devices that you guys are worried at the device level, if we can use those really as the way to get the data from the sensors to something like the Snowball, where those queues are running, we get all the security that comes with the rest of the AWS platform. We don't have to reinvent that wheel. Yeah. We can use the Snowball to really add horsepower and add security to a lot of the workflows that we have.
Yeah, and then essentially you're taking that edge device and it's handing you a 1 or a 0, which isn't that sensitive.
Yep, and in addition to that, right, I mentioned our partnership with Unveil. When we do want to do something like a cross-domain solution and send sensitive information from one of the models or one of the sensors back to a more sensitive environment, that kind of encrypted pipeline really helps us with that, and we're really excited about that. Any other questions? Thank you all so much.
Yeah, and if anyone wants to run up, you can.